All right, just waiting for everybody to get back to their seats to get started with the team. This year, the team is going to be, their team name is the Water People, and they are going to be presenting on the development of a stormwater management model to mitigate the effects of increased rain intensity from climate change in the Almendrades watershed in Havana, Cuba. I'm more than happy to present Alex Rodriguez, Jasmine Perez, Miguel Armesqua, and Eugene Victoria. All right.
Thank you, Regina. Good morning, everyone. Thank you very much for being here today. We are the Water People from the University of Miami, and today we will be presenting the stormwater modeling of the Almendrades watershed in Havana under climate change. First off, to introduce the team, my name is Miguel Armesqua. I am a senior at the University of Miami, majoring in civil and architectural engineering, and I was born in Havana, Cuba, in the Almendrades watershed.
Hi, my name is Jasmine Perez. I'm a junior studying environmental engineering, and I'm from Miami, Florida.
My name is Eugenio Victoria. I'm a civil engineering senior at University of Miami.
And my name is Alex Rodriguez. I'm a sophomore majoring in environmental engineering at the University of Miami, and I'm from Miami, Florida.
Thank you, Alec. So our objectives for today's presentation are, first, I will discuss the significance of climate change on the city of Havana. Then, Jasmine will discuss how we gathered and collected watershed data in order to use in a model that will forecast how climate change can affect the city of Havana. Then Alec will discuss how rainfall was quantified and adjusted for climate change, then how the model was applied and the results we obtained from the model. And last, Eugene will discuss a solution which we propose in order to control urban runoff and flooding in the city of Havana. So to begin, according to NASA, sea levels rose 7 inches in the last century. This poses a major threat to coastal cities like the city of Havana and the city of Miami Beach, which we know occasionally flood. Also, 2015 was the warmest year on record. You may recall New York City experiencing 70 degrees on Christmas Day. On top of that, the frequency of extreme weather events has been increasing. Phenomena like El Nino and the recent Hurricane Alex, which formed over the Atlantic 2 months after the end of hurricane season, are showing signs that the climate is changing. So what does this mean? Well, climate change will cause more intense rainfall. Greater frequency and intensity of rainfall will lead to more urban runoff and flooding. Urban runoff is caused when rainfall does not infiltrate into the ground and there are differences in elevation in the surface causing the water to flow. And when it accumulates excessively in any given area, it leads to excessive flooding. Also, by 2030, global economic losses from flooding will increase from 90 billion to 500 billion. And according to the United Nations and the recent COP21 conference in Paris, climate change is one of the largest threats that humanity faces today, especially for developing countries like Cuba. Because of Cuba's developing economy, aging infrastructure, and in particular Havana's high urbanization and it being a coastal city, it is extremely vulnerable to climate change. And unlike the United States, Cuba does not have flood insurance or an organization like FEMA. So any damage incurred from flooding will be extremely difficult to recover from. And we have seen what flooding can do to cities like New Orleans and New York. And Cuba is definitely not prepared for an event like this. So it is extremely urgent and critical for Cuba to begin to plan and adapt for climate change. And now, Jasmine will discuss the data analysis.
Thank you, Miguel. So the first thing that we had to do was obtain and analyze a variety of data. Our two main sources of data were our digital elevation model, or DEM, and our Landsat imagery. A digital elevation model is a grid-based data representation that has an elevation value in each point of the grid on the map. Using our digital elevation model, we were able to delineate our watersheds and then find our elevation data as well as characterize our subcatchments. Our other main source of data was our Landsat imagery. We used an image from the Landsat 8 satellite, which is a satellite run by NASA and the United States Geological Survey. Using that imagery, we were able to visually analyze the land use and then use those three forms of data to input into our runoff model. So to delineate our watersheds, we put our digital elevation model onto ArcGIS, which is a geographic information system that's used to manipulate a variety of different kinds of geographic data. We were able to find the directions of water flow in different areas and find the general shape of the Almendares watershed, which is shown right here. The Almendares watershed can be further broken down into the upper and lower watershed. We chose to focus on the lower watershed because it's highly urbanized and has greater potential for runoff and flooding damage. We then continued to delineate into sub-watersheds or subcatchments because there's a greater computational accuracy from using the smaller areas rather than the whole watershed. The next step that we had to take was find a variety of junctions, we broke the subcatchments up into 3 different regions. The red region is the ocean region because it's nearer to the ocean. The yellow region is the lower region because it's in the lower Almendares. And we called the green region the upper region because it's nearer to the upper Almendares watershed. The next step that we need to take was to locate a variety of junctions. The junctions were the locations at which streams and other bodies of water flow connected onto the main path of the Almendares River. So using our DEM, we were able to find those locations, which are indicated on this map with the blue points. We then needed to find the invert elevations at each of those junctions. The invert elevations are the below-ground elevations at the bottom of the channel where the water flows through. So using our elevation data, we were able to subtract to find the approximate elevation. The last step of our data analysis was our land cover analysis. Using the Landsat imagery, we were able to visually analyze to determine which areas were urban areas versus which areas were non-urban areas. The reason that this is significant is because urban areas typically have structures that are made of materials that are more impervious, such as concrete, so the water can't permeate into the ground and it runs off or flows. The red areas indicated in this image were the urban areas, and we calculated the percentages of urban areas in each of the subcatchments. We were then able to use those percentages in our imperviousness calculations, which we put into our model. And now to discuss our model is Alec Rodriguez.
Thank you, Jasmine. So we have all this data. We have this watershed data, this elevation data, and the land use data. And we need some way which we combine it all to create some sort of model that will model the watershed and determine how the water runs off in each subcatchment. So to do that, we utilized the Environmental Protection Agency's Stormwater Management Model 5, also known as SWIM5. SWIM5 is a hydrologic modeling tool that consists of 2 parts, a runoff portion and a routing portion. The runoff portion utilizes all that data we collected, the watershed data, the elevation data, and the land use data, and combines it so it determines how much runoff occurs within each subcatchment. This then translates to the routing portion, which utilizes a system of user-created pipes and channels with which to transport the water. So if we look at this image here on the screen, this is what I like to call the skeleton of our model. This is just the model itself without any sort of background imagery. And so you can see we have these funny shaped polygons. These are the subcatchments. Each black box is just the centroid or center of mass of each subcatchment, and they all lead to these black dots. Those black dots are the junctions. And we can see we have a black line snaking throughout the middle of it, and that black line is just the Almendares River. For our purposes, there's no actual river modeling within SWIM5, so what we did was we modeled the river as an open trapezoidal channel to best mimic the river geometry. You can see on our poster as well, this is what the model actually looks like within SWIM5. So we have a model, which is great, but now we need rainfall because you can't have runoff without rainfall. So what we did was we initially looked at Cuba's rainfall data, and Cuba has monthly rainfall data, which was not good enough for what we needed because we need to find a very strong storm with which to test our model. So what we did was we saw that Cuba's data was comparable to Key West's, and then we saw that Key West was comparable to Miami's. And so we looked at 60 years worth of rainfall data from Miami International Airport and found a storm dated April 25th, 1979 that ranked very closely with the standard storm used when modeling stormwater management systems. That storm is a 100-year, 24-hour storm, which is a storm that occurs once every 100 years and lasts for 24 hours. So it's a very strong storm. But we can't just settle with that because we're talking about climate change, we're talking about the future. And so we need some way with which we can quantify how much stronger will the storm be. So we utilize the SWIM Climate Adjustment Tool, which is a tool that utilizes data from the World Climate Research Program, which is an organization headed by the United Nations. And what this does is SWIMCAT utilizes these adjustment factors obtained from the program as well as future climate projections to quantify how much strong storms are going to be. So if you look at our bar graph here, we have the gray bars. That's the rainfall from our April 25th, 1979 storm. And then if you look at the blue bars, that's our climate-adjusted storm. So we can see it gets significantly stronger. So we recognize that there's going to be a problem. And let's see how this plays out within SWIM. So if you look on the right of the PowerPoint, you can see we have an image. That image is of the Almendares River. And if you look at the banks, they are very shallow. It's not going to take a lot of extra water for these banks to overflow and flood. So we want to head this problem off the source and deal with the runoff so that we avoid that problem. And so we ran some SWIM 5 once, and you can see the resulting hydrograph on the left. The blue line indicates our pre-climate change flow, how much runoff is occurring with our April 25th, 1979 storm. We then ran it again using our adjusted storm through SWIM 5, and we see we have the red line, which is our climate-adjusted flow, and it's significantly larger. So we have this problem. We have an increase of runoff for a system that probably is not able to handle current loads, much less future loads, which are going to be significantly larger. So we need some sort of solution with which we can mitigate and control runoff. And to discuss that, here's Eugene.
Thank you very much, Alec. So our model was executed for 2 different storms. One being the 1979 storm, the 100-year storm, and the climate-adjusted storm. The climate-adjusted storm had the same rainfall intensity as the 1979 storm, or the 100-year storm, plus the added effects of climate change. And our particular stormwater management method that we chose to use was the detention basin. And what a detention basin pretty much is that it's a bioinfiltration cell that holds excess stormwater and then waits for water levels in the receding channel to decrease, which at that point it transfers the water over through a pipe or drainage system. And as you can see, a detention basin can really reduce peak flooding, which is one of our objectives. And we inserted the detention basin into 2 subcatchments. Here we have subcatchment 05, the urban subcatchment. And we chose subcatchment 05, as you can see in the map, because of its proximity to the coast and its high imperviousness. And here's a runoff hydrograph extracted from the very versatile SWIM 5 model. And a runoff hydrograph represents the amount of runoff per time in response to a particular rainfall amount. And this is really important because as large amounts of runoff collected from total aggregate sources, that can cause flooding, so therefore that should be prevented. And as you can see, the red presents the subcatchment 05 runoff, and the peaks are very high, and the detention basin outflow, the peaks are much lower and neutralized. And you can see the drop is almost 75%, which is enormous, and it also represents an important visualization to our project because it shows that a detention basin can control flooding and also reduces runoff, which is one of our objectives. And then in the next slide, we chose to use subcatchment U4, as you can see in the map, because to show the detention basin can work in an urban as well as a rural area. And as you can see again, the peaks are much lowered, almost by 50%, and the peaks are subsidized and neutralized. So the reason that we chose the detention basin as a particular stormwater management method was not only because of its ability to reduce flooding, but also because of its several practical advantages as well. And some of these advantages include that it is cost effective, it improves water quality, recharge aquifer, and has multiple uses such as parks, and has worldwide applications as well. And for the water quality sense, how it addresses water quality is that a lot of times urban runoff from mountains carries a lot of contaminants. And if you give the detention basin the opportunity to remove those contaminants and address water quality, that serves a very important use. And the main goal of the detention basin is to coexist with the community. And that serves in the best interest of our model and really the best interest of the Cuban people. And here are the objectives. And as you can see, we discuss climate change's significance. We analyze watershed. We quantified rainfall just for climate change. We applied the runoff model, and we proposed control for urban runoff. And we would like to thank the team and everyone that helped us. And we would like to address any questions at this moment. Thank you.